I almost forgot. I totally forgot. Thank you so much. Okay, so we're doing unit tangent vector. And so the definition, provided that your r prime isn't equal to 0, is this right here, big T, unitized derivative. That's all it is. It's a unitized derivative, but we call it big T. So we're doing an example right now to find the unit tangent vector for this guy. Here's the derivative. Here's the magnitude. Unitize it. Okay. And then please distribute the scalar portion there. And we're done. We just found the big T. Fantastic. Wow. So now what? Well, they did want us to evaluate it at time t equals 1. Okay. So if we do that, let me just continue down here. At time t, and I'm saying time because usually the parameter t is time. Not always, but a lot of times these vector valued functions are used to model motion. And so typically, traditionally, the parameter t represents time. So we're just going to substitute a 1 in place of the time for our unit tangent vector. And we'll substitute a 1 in there. Fine. And then what we'll get is a constant vector. 1 over square root of 5, 2 over square root of 5. Boom, there it is. Now, if you were to graph that in standard position, which means, the initial point is the origin, you would find 1 over square root of 5, 2 over square root of 5 like that, and you would then draw a vector to it. But if you're doing the thing that we did last time, where you're basically corresponding this vector to the point on the curve that corresponds to, the point r of 1, so the original function is right there. And so the t of 1, you see this little vector here, you lift this thing up, you translate it so it's moved over where it's corresponding to the point. And I hope you can see that this vector, this little unit tangent vector, is in fact tangent to the curve that it corresponds to, that point when time t equals 1 second. Okay. So let's fill in the blank and complete this sentence. The tangent line to a curve. So now we're talking the tangent line. So if I draw the tangent line at this point, that's a terrible straight line, but I think you get the point. So the tangent line that passes through the point, and it's going to be parallel to that unit tangent vector. In fact, if you had to come up with the parametric equations for that tangent line, you could use this unit tangent vector, big T, as the direction vector for that line because it's parallel. So any questions so far? We just finished example 1. We found big T, the unit tangent vector, and we evaluated him when time t equals 1 second. Okay, now let's do one in 3D. That was a 2D example. We'll do one in 3D. Fine. So this position function here, this vector valued function, if you graph it, it's one of these cool looking helixes. Remember we kind of looked at one of those before? It's kind of fun. And they want big T for that guy. And then they want us to evaluate big T when time t equals pi fourths, okay? So when t equals pi fourths, if you do plug that into the position function, you're going to get the point on the curve right there, and it's going to have these coordinates. Okay. And they draw a picture of the tangent line here. Great. So the tangent, the big T is simply going to be a vector that's parallel to that tangent line. So if we were to draw that, it's just going to be a unit tangent vector like that. I could even draw it right now, but let's actually go get it. So big T is going to be equal to what? It's going to equal the unitized version of the velocity vector, the derivative of the vector valued function. So let's go get r prime first, and then we'll put it all together. Easy peasy. Okay, the derivative of 2 cos, minus 2 sine. Derivative of 2 sine, okay, 2 cos. The derivative of t, 1. Great. And then let's go get the magnitude of that. so that it'll help us unitize square root of the sum of the squares of the components. And then I'm going to do a little bit of cleanup here. Do you notice anything that we can do using a trig identity here?
You can simplify.
Mm-hmm. So what do you think I should do to simplify?
Factor out the 4 and then use the trig identity of sine squared plus cosine squared.
Yes, perfect. And so that's going to be a 1. And so we really have 4 plus 1 underneath the radical. Oh, we get a constant. That doesn't always happen because we saw in the previous example, the magnitude of the derivative wasn't just a constant. Look at this guy up here. We got that. That was just, is basically those components are functions of t. But so that where the denominator there isn't a pure number. Here it just happens to be a pure number, which is nice. And now you can put big T together because you're going to unitize this derivative. Okay. And we'll divide everything by square root of 5. Fantastic. And then when I distribute my scalar, oh man. Technology, you can't live with it and you can't live without it. Okay, and they wanted us to evaluate when time t equals pi 4, so we got to finish up the problem. Okay, so I'm just going to substitute time t equals pi 4 seconds into this. Oops, did I forget my sine t there? It didn't show up, sorry. Didn't show up. Okay, now we can substitute in pi 4, so we've got -2 sine of pi 4 all over square root of 5. And then we've got 2 cos of pi 4 divided by square root of 5. And then the last component is just a constant, 1 over square root of 5. And then sine and cosine of pi 4 is just a nice number, isn't it? Well, it's not that nice, but what is it? Anybody know off the top of their head what
Over 2 over 2.
Yeah, it's going to be root 2 over 2. Very good. So when we do that, our and then I'm going to reduce. So these 2's are going to cancel. Like this is square root of 2 over 2. And then do a little bit of simplifying. You'll get negative square root of 2 over square root of 5, comma, square root of 2 over square root of 5, comma, 1 over square root of 5. Boom. There is your big T at this point right here on the curve when that time t is pi 4 seconds. You do not have to rationalize any denominators for me, okay? Not even for my math lab. My math lab will be totally fine with you plugging in or typing in that answer, so don't bother. Now, if some of you are like, well, I don't like seeing radicals in the denominator, and you want to keep going, fine. My math lab will accept that answer also. Either one. But I don't like to waste valuable time. If I don't have to rationalize the denominators, why bother? Right? Questions? Everybody okay? Are we alive today, even though it's a Friday?
Yes.
I'm not. I want to go back to bed. No.
I'm like, I was like, sure didn't panic because of the quiz. I don't know why though.
Oh, okay. So which quiz are you panicking about?
Oh wait, no, not the quiz, the exam.
Oh, you're panicking about the exam. Well, you know what that means, Nathaniel? That's actually a good sign because it means you care.
I mean, yeah. It's like I had to juggle like studying for a quiz for chemistry too.
Oh, yeah, that's the crazy life of a student.
Yeah.
They're always having to worry about exams. Hopefully it's not on the same day, is it?
No, thank God that one actually did it
thank God.
yesterday.
Oh, okay. So now you can just focus on Calc 3, right?
Yes.
Yay. Okay. Well, I wish you luck on that chem exam. Hopefully it was okay.
Yeah.
Okay. Let's take a look now at example 2. what about this big T? You know, there he is, this little red vector. What if we wanted to come up with a vector that's orthogonal to it? And like, why would we care about doing that? We'll get to that. But it turns out in 2D, if you're in 2 dimensions, let's say you had a curve like this, and you had a big T, I'll just pick a point. Here's a point. And let's say, you know, this is the graph, say, of some vector valued curve that's 2D. And you picked a point there, the unit tangent vector would just be, you know, a unit vector like so, tangent to the curve. So if you're in 2D, here's a cool thing. There's only 2 possibilities for the vector that would be orthogonal to big T. One possibility would be pointing that way, and the other possibility would be a vector, I'll use a different color here, pointing this way. So you have 2 choices. Now, what we're trying to get right now, there's only one of those that's going to work. But I'm just pointing out in 2D, you only have 2 possibilities. But what about if you're in 3D, like this picture here that we just finished? Here's your big T. You could go, well, if I point that way, it's orthogonal, or if I point that way, it's orthogonal. But what if I am pointing coming out of the page? Coming out of the page would also be orthogonal to that little red vector. And I claim there's infinity possibilities, you know, pointing out of the page, as long as it's making a 90-degree angle, you know, it would be orthogonal. So it turns out there are infinitely many vectors that are orthogonal to the tangent vector in 3D. In 2D, you only have 2 choices. But one of these, it turns out, is the vector T prime. Now, why would that be? Now, this is the cool thing. If you recall from a previous theorem, and I know you probably forget, but this theorem said the following. This is from like a week or 2 ago. If the dot product of a vector with itself is equal to C, some constant, then what is going to be true is the dot product of that vector valued function, or whatever it is, or that vector, with its derivative will be 0. So in other words, they're orthogonal to each other. The vector with its vector valued function with its derivative. Do you guys remember this theorem? Sort of?
Yes.
I actually proved it. In fact, I'll prove it again. Here, if you're given this is true, if you take the derivative of the dot product of R dot product with itself, and you take the derivative of the right-hand side, that better be equal. Well, the right-hand side, the derivative of a pure number is just 0. Here, I'm going to use the product rule. Remember we did this? I think we did this the other day. And you had R prime dot product with R plus R dot product with R prime. These are like terms, so you can add them. So you've got 2 of those, dot product of R with R prime. And then you just divide both sides by 2, and voila, the dot product of the vector valued function R with its own derivative is 0. So that had to be true. So what does this have to do with this fact right here? I'll show you. I'll keep going. So we know that this big T is a unit vector because that's the way it was defined. That's true. When you take the dot product of big T with himself, there's another theorem that we did about 3 weeks ago that says the dot product of a vector with itself will give you the same thing as, oops, not with a prime, sorry, bad notation. That is the same as the magnitude squared, but that's just going to be 1. So we just showed that the dot product of this vector value function T with itself is 1. Therefore, it's got to be true that the vector valued function T dot product with itself will be equal to 0. So that's why we can say that T prime is definitely going to be orthogonal to T. Now, if we normalize, which is a fancy word for unitize, the vector big T prime, you obtain another special vector, special to Calc 3 as well as physics. the principal unit normal vector. Fill in the blank here. The principal unit normal vector. Yeah, what about it? Here's the definition. Right here. And we call him big N for normal. And it's just the unitized big T prime. That's all it is. As long as big T prime is not the zero vector, of course, because that would not work. So there's your big N. And you're guaranteed that big N is orthogonal to big T. Now, as I mentioned, if you're in 2 dimensions, it's kind of easy to get big N. You don't have, if you wanted to cheat and get it, because here at this picture, I'm just showing you there's big T, and big N could either point in or back out. And it turns out the reason why they're showing it pointing in is because that's the correct choice. You want to notice that big N is always going to be pointing towards the concave side of the curve, or pointing in the direction that the curve is turning. And let me write this down. Well, this is part of it. They're telling you right here. It points toward the concave side of the curve. That is, it points in the direction the curve is turning. So if you were driving on this curve with your car, let's say right here, you're driving, you're cranking your steering wheel a little bit to the left. And so that means that you're going to have to choose the left pointing vector that's orthogonal, the big T, and not the other one pointing the opposite direction, because that would not be in the direction the curve is turning. Okay? So you want to do it in the direction the curve is turning. Fine. So if you had your big T, there's only 2 choices that big N could be: negative y, x, and you can test at me, take a look at what big T dot product would N would be. It would be 0 if this were your big N, but the other choice would be y of t negative x of t. And for this picture that I have here, just for this picture, only one of these is going to work. And it's actually going to be this one for that right there. Okay, but in 3D, you can't use this trick. Sorry. Because there are infinity different ways that the big T's orthogonal vectors can point. But the big N will still point in the direction that the curve is turning. So you'll notice here, they're showing you a little example. Here's your curve, tootling along there. Big T at this one point, it's tangent, and big N is pointing in the direction the curve is turning. Now over here, if we were over here at this point, big T would still be tangent, but big N would point in the opposite direction because the curve kind of is turning in the other direction. Okay, so that's just a nice picture, and we're done with that. Now let's talk about one extra thing here, big B. Binormal vector, big B. Our physics brethren are really into big B. They're into T and B, all 3. So this binormal vector is defined to be the cross product of big T and big N. So it's orthogonal to both big T and big N. And because you can have T and B at various points in a curve, so let me just show you here. Let me get rid of all this. Here. So where would big B be pointing? Well, big B, if you did the cross product of T and N, big B would be pointing this way, up, because he's orthogonal to T and N. And what physics people are really into is no matter where you are on any point of the curve, let's say I'm right here, you've got your T, you got your N, and then big B, follows along. So you have something called the TNB frame. The TNB frame. I don't make this stuff up, people. I report it. Physics people are really into this TNB frame. And the TNB frame plays an important role in the branch of mathematics known as differential geometry, and it has an application of the motion of spacecraft. So you should care about that. And when I was an engineer at General Dynamics many years ago, we would have to worry about this sort of idea of pitch and yaw of the aircraft, or the spacecraft, depending on where our circuit was going to be placed. And it had to pass what we call military spec, or mil spec. So when you would do a test drive or test flight of your circuit board, they would stick your, I used to do digital circuit hardware design. They would stick your board in like, a test aircraft, send it up over the test pilot, and they would do various things. They'd have to rock it forward and back, that's pitch, and then rock it side to side, that's yaw. Pitch, yaw, and then you'd have to have a combination of pitch and yaw. Woo! And if your circuit like crapped out for any reason due to either pitch or yaw, it failed and you had better go fix the problem. Good times, good times. Okay, any questions so far? We're going to go get big T, big N, and B right now. We're going to do a T and B problem. Here we go. T and B. Okay. You know what? I'm going to have you guys do the big T and the big N. Well, let's have you do big T. Let's you do this, right? Okay. Find big N. No, hang on a minute. I already got big T. Never mind. Never mind. I can't do that. We already got it. We're continuing from a previous example. Sorry. I'm going to make you do something today. I want you to work. Okay. We already got that big T for this same problem. We did it already. Previous example. Really? It's the same one. It's the same original position function. So when we did example 2, way back here, that it's the same function that we're starting with. So we did get big T already. I don't want to have to get it again. He's right here. So I'm just going to copy that down, and then we'll get his big N and big B. Okay, fine. We got all this stuff going on here. All right. There's big T. Just copy it down. Okay. Now you're not going to like this part, because especially when we have to unitize this puppy. It's not too bad for this problem, but it could be worse. So first you go get big T prime, which for this problem is not too bad, because you're just taking derivatives of sine and cosine. How bad could that be? So you go, okay, derivative of the first component is going to be what? -2 over square root of 5 cos. And then when we take the derivative of cos, we're going to get a negative sine, and then the last component just has a derivative of 0 since it's constant. Great. Now go get the magnitude of big T prime. Okay, so you're just going to take the sum of the squares of these components underneath the radical. And I'm purposely ignoring the negatives because I know that when you square a negative, you're going to get a positive. So now this is going to be sort of a hot mess here. I'm going to factor out the 4/5 because then I have that cos squared plus sine squared, which is 1. And then the square root of 4/5. You could go a little bit extra using a law of radicals. Simplify it a bit. It's 2 over square root of 5. Okay, now you're ready for big N, this principal unit normal vector, because it's the unitized big T prime. It's the unitized big T prime. Woo, sorry. Unitized, and we just got big T prime, so we have him as -2 over square root of 5 cos, -2 over square root of 5 sine, 0, and we're putting him over this magnitude, and then clean this up. You know, dividing by 2 over square root of 5 is the same as multiplying by the reciprocal. I'm running out of room here, aren't I? And then distribute the scalar and then clean it up. And after you reduce your big N, oh, it doesn't look too bad because you simplify these components. Nice. So there's big N right there. We got him. So good news. We got the unit tangent vector from before. We now have a vector that's orthogonal to big T. It's called big N. That's also a unit vector. And now it's time to get big B. So big B, the binormal, is defined as the cross product of big T and big N. So I'm going to use this 3x3 determinant method to get the cross product. You know, it's kind of a mess, but it's going to turn out to be not too bad because one of these elements is 0, so that makes it kind of nice. So I'm going to do this on the fly. You're going to go this times this, which is 0, minus this times this, which is what? -1 over square root of 5 sine, but then a negative is a positive, so that's going to be your I. minus, and then you're going to go this times this is 0, minus 1 over square root of 5 times negative cos j, and then plus, and then lastly, you're going to go, okay, this one's not going to be too fun. You'll have a negative times a negative, which is a positive, sine squared t, and then minus a minus, which is really a plus, 1 over square root of 5. Did I forget something there?
Professor,
Yeah.
isn't that negative directly under J?
Sorry, I'm a little bit confused as to what you're asking there. I'm
The
sorry.
the 2 root 5 sin t,
So
is that negative?
I'm still, can somebody help me out and let me know, are you talking about this right here?
I think in the matrix, the IJK, it's -2 square root 5 sine t. I think he's
Okay.
saying that the j is supposed to be negative, but I think it's actually just supposed to be cosine t instead of sine t.
Yeah.
Okay. Did I copy it down wrong?
I
Is that
think
what
so.
you're saying? Yeah, I think I did. Yes, you're right. Thank you. Okay, so in the second row of the matrix, I apologize. I think I copied down the second component of big T. I accidentally used sine. Okay, so I apologize for that. So let's see. I have my I is good, and then sine squared here, 0 minus. That looks good. Okay, and then for the last guy, I've got, okay, I do have a sine squared. There we go. That's better. So then I have this times this, which is positive 2 over square root of 5 sine squared minus, and then we're going to have a minus minus. So that's why I got the plus here. And then we'll have 2 over square root of 5 cos squared. Okay, now this is working out to what my notes are. Whew, I was wondering what the heck happened. Let me rewrite it in component form just because it looks prettier. So I'm going to have a positive sine t over square root of 5. The second component, we've got a minus minus here, but then that is another minus, so that is going to be negative. Cos t over square root of 5. Woo! And then this last term, if we factor out 2 over square root of 5, the other factor is sine squared plus cos squared, but we know that adds up to 1. So we'll just have the constant 2 over square root of 5. Whew. Okay, now what about this big B? This is big B here. This is a vector that's normal. It's a normal vector to the plane containing T and N. So that's kind of interesting. So in other words, like if your T were like, I'm just making a little picture here on this side margin. Let's say T were pointing that way, like out of the page, and then N is orthogonal, you know, making a 90-degree angle with big T. Then you can think of these guys being in a plane. The B vector is a vector that's normal to the plane that would contain T and N. So it's orthogonal here. There it is. And that's sort of the important concept. Now, they did ask us to evaluate at time t equals 0. That was the last part of the problem. So no problem. We know that if they wanted us to find an equation for the plane. Let's look at they said, find an equation for the plane containing T and N at the point when T equals 0. So the B that we just got is a normal vector to the plane. And we only need one more thing to get a plane equation. You know, a point on the plane, right? How? Anybody have an idea how I'm going to get a point on this plane?
Don't we plug the t equals 0 into r of t?
Very good. R of
To get the
0. Brilliant. Brilliant. That's perfect. Exactly right. That is going to give you a point in that plane. And so I get, what do I get here? Let's see, cos 0 is 1, sine 0 is 0. So I get this point. And then, folks, I know that some of you have been following Briggs, the view an example button when you did your quiz 3. And I gave you credit, but I really wish you would do it my way, which is the standard equation for a plane, which let me remind you, looks like this. So on quiz 3, I know that some of you didn't use the standard equation for the plane, but I may ask you for the standard equation on let's say midterm 1 Monday. And if you give me the ax plus by plus cz equals d, which is the general equation for a plane, and most of the MyMathLab problems want it in this format, but what if I did ask you for the standard equation? It looks like this. So the A, B, and C are the normal vector components. So I'm going to have to evaluate this B at 0 to get the normal vector at that point. The A, B, and C. And so it looks like that's going to give me what, 0. Running out of room here. 0, -1 over square root of 5, 2 over square root of 5. But what I'm going to do is I'm going to just multiply this by square root of 5 and just use, because I can use any multiple for my normal vector. So the A is 0, so it doesn't even matter. So here I'm just going to have 0x minus 2, fine. And then the B is -1. I could use -1 over square root of 5, but I'm going to just use a multiples of that guy. And then y minus 0 plus 2 times z minus 0 equals 0. And then cleaning this up a little bit by distributing, I'm going to get -y plus 2z equals 0. And there is the equation for the plane that contains big T and big N. Now, in the world of physics, they have a special name for this plane that contains T and N. I don't make this stuff up, I just report it, okay? It's called the osculating plane. Osculating plane. I know, weird, huh? Okay, how about if you guys find big T and big N for a problem? I'm just gonna cook something up and put you in a little breakout room and make you do it. What do you think? You think you handle that?
Sure.
Sure, why not? I like that attitude. Okay, so this is not in your course reader, but I want you and a buddy to take a look at this position function. R of t equals what the heck? 2t, 3 sine 2t, and 3 cos 2t. That's a beautiful position function, all right? It's lovely. Now, what I want you and the buddy to do is go get the unit tangent vector, and that's also known as big T, okay? And just get the regular unit tangent vector. Don't evaluate it at any t. And then after you're done with that, if you feel bold and courageous, also go get the principal unit normal vector, which we call big N. Big N, okay? So if you feel bold, go for both, okay? But I'll be even happy if you can just get the one. It's not too hard. I think you can handle it, all right? So let's see, we've got, gosh, looks like we're missing somebody. What the heck? Okay. I'll put you in 5 breakout rooms. One of the breakout rooms will have 3 people, so you and your buddies go try this. Please turn your mics on. Appreciate that, because, you want to be able to chat with your buddies. It's easier. It's hard to do in a chat box sometimes, especially when you're discussing math, All right, we'll see you later. I'll come visit. Join your breakout room, folks. Join your breakout room.
Hello?
Jake, are you there? Jake, are you there? Hello?
Can you hear me?
I can kind of hear you, but your mic is all, sounds like you're talking in from the end of a tunnel or something. Yeah, I can hear you a little bit, but not much. I put you in a breakout room. What happened, Jake? You disappeared on me. Well, I tried to put you in a breakout.
Wait,
Yeah. Well, I tried to in another breakout room, but then you
can you
disappeared.
hear me?
Yeah, but not very good. It's like, mm-mm. Okay. So I'm hoping that you got a little bit of access to what finding big T and big N involve. And so what a big mistake that some students make when they're finding big N, usually people get big T pretty well. That's like, okay, got my big T. And they wrongly think that they just have to unitize the acceleration vector to get big N. So you have to be very careful. So even though it is true that big T is equal to the unitized derivative, you have to be careful because big N is defined as big T prime getting unitized and not, be careful, big N is not, this is a not equal sign, equal to the second derivative of R of T getting unitized rather. This is no bueno. Okay, but some people go, oh, I'll just do that and I'll get my big N. No, you won't even be close. Okay, so be careful. That's a common rookie mistake to make. Big N, you have to get your big T and then you have to get the derivative of big T and unitize that, not the second derivative of R prime or R rather, and then unitize that. So this is not good. Don't do it. Okay. Just a little tip. I'm hoping nobody did that. I didn't see anybody. Well, I didn't see a lot of what your work was doing, but it's like, it's really hard to teach remote. You know what I mean? It's really hard. Okay, so let's see what happened here. So for this problem, I'm hoping that you got your R prime. Let's see if anybody got this. I don't even know what the answer is. Okay, I just kind of like, hey, here it is. Here's a problem. Let's just give it a shot. So hopefully you got your R prime looking something like this. Does that look right? And then when you got the magnitude of it, you just took the square root of the sum of the squares of the components. And then after you cleaned this up and you factored out a 36 from the second term and the third term, you notice that this added up to 1, hopefully, and then you just got the square root of 4 plus 36, but that's the square root of 40. Now, in this class, anytime you get a radical, if you can go a little bit extra for me, since 40 is the same as 4 times 10, and there is a perfect square factor in there, that is your R prime's magnitude. And now you can put it together because big T is the unitized R prime. Yay! And so what you're going to have here is, okay, look somewhere else here. Your R prime was what? 2, 6 cos, negative 6 sine. And when you divide that guy by 2 square root of 10 and then use scalar multiplication, you should get the clean version after reducing that looks like this. Did anybody get this for big T? Anybody get this? Yes,
Yes.
no? Okay.
Yes.
If you got that, congratulations. Yay, success. Woohoo! Now the hard part. The hard part is always trying to get big N because it's like, it takes some time and it can be tedious. So once again, just to remind you, big N, you don't go get R double prime. No. You got to get T prime and then unitize that. It's like, okay. So let's get big T prime first because we did get big T. Here it is. And we're just going to take the derivative of that guy. Well, good news. The derivative of a constant is 0. Hey, that was nice. And then the second thing is taking the derivative of a cos, which is going to give us a sine. And then taking the derivative of a negative sine will give us a negative cos. And I think we've got big T prime there. That look good? So if you clean it up a little bit, you're going to have negative 6 over square root of 10 sine of 2t, and then negative 6 over square root of 10 cos of 2t. Okay, that's big T prime. But to get big N, you need to unitize big T prime. So now let's go get the magnitude of big T prime. Yeah, it's going to be pretty gross. Well, 0 squared plus 6 over square root of 10 sine 2t squared plus 6 over square root of 10 cos. I'm doing this really fast here. Squared. And then once again, if you notice that those terms are going to have a common factor of what, 36 over 10. Ooh, nice. And then of course, this is adding up to 1 from your trig identity. And then square root of 36 tenths. Ugh. It's not a real nice thing, but what the heck? Looks like that. Did anybody get that for magnitude of big T prime?
Yes.
Fantastic. So now you're ready to put it together. And since dividing by a fraction can be turned into a multiply by the reciprocal, I'm going to immediately multiply my big T prime here by the reciprocal of 6 over square root of 10. And something nice is going to happen. I hope you can appreciate that. Because you can reduce a little bit when you distribute this scalar. And so hopefully your big N, if we're all on the same page here, right, is just turning out to be this. Is that right? Anybody else get that?
Yes.
Yay, success. Okay, I'm going to start arc length and we'll do an arc length problem or two. Okay, so hopefully everybody got on board with the big T and the big N. It's not really hard, but you got to know how to do it. Okay, now what? So can you use this for anything? Well, we will in a little bit. Arc length and curvature is next. So I want to do arc length first because you actually have already done arc length. Really? Yeah, you forgot though probably because you probably did it in the very last day of Calc 2. So if you remember from Calc 2 when you did parametric equations like the last week or two, and in Calc 2, one of the things they do at the very end of the semester is you use, doing those parametric equations, you learn an arc length formula. And the arc length formula you used in Calc 2 is this. This is it right here. So you did this in Calc 2. I'm not making this up, people. I know you probably forgot. That's okay. Don't worry. But this is still good. So in other words, if you have parametric equations or a vector valued function that you can create out of those parametric equations, the arc length of that curve, so if you graphed it like, and you wanted to know the arc length from time t equals a seconds to over here, say time t equals b seconds, you're like, hey, what's the length of that arc? If you had like a flexible yardstick or something or flexible tape measure, it's this. Now in 3D, you just extend it. You just take the square root of the sum of the squares of the derivatives. And I do want to say that what I want you to notice is this is speed. What do I mean? It's the same as the magnitude of your velocity vector. That's all it is. Same up here. They didn't tell you that in Calc 2 though. In Calc 2, they didn't want to, talk about vector valued functions. But we do here in Calc 3. So what am I saying? Arc length is essentially taking the integral of speed. Yeah. Okay, fine. Let's go get arc length of this curve. Do you recognize this?
Did we just do that?
Yeah, you just did it. I just made you work on that function. I made you go find big T and big N. Congratulations. So the good news is we already have our prime. We already have the velocity vector because we did that. So I'm just going to copy it down. And then we already got the magnitude, which is speed. So we already got square root of 40, remember? So the arc length, which is usually most math books will use lowercase s. I'm not making this up. Lowercase s means arc length. Remember that because we're going to need it for the rest of the semester. Yes, we're going to use arc length. It's going to come back around again. It's going to be the integral going from 0 to 2 pi because they gave us the time interval of speed. And this is kind of an easy problem because speed turned out to be a constant, which is really awfully nice. That doesn't usually happen, but hey, when it does, it's cool. And we're like, oh man, come on, this is an easy integral. You're just going to go, okay, this multiple 2 square root of 10 times t, where t gets evaluated between the limits there, 0 to 2 pi, but that's 2 square root of 10 times 2 pi. And ultimately, we get 4 pi square root of 10. And we're done. That's the arc length. Now, folks, arc length always has to be a positive result. If some weird thing happens, you get a negative number, try to look for your silly mistake somewhere because it means you made a silly mistake. So be careful. Arc length must be positive. And that makes sense, hopefully, because it's a length, right? So let's do one other problem of arc length, and then we'll be done for the day, okay? And then you're going to go have a great weekend and study. I have office hours today from noon to 2. So if you have any last minute questions you want to come on down. Okay. Last problem. Check out this baby. Oh God, are you kidding me? How do you get the arc length of that beast? Well, you got to get the R prime to get arc length. And you are going to have to use the product rule on that term. And in the second component, you'll also have to use the product rule on that. So, oh man, you're going to have to use the product rule all over the place? Yes. Okay. I love the product rule, people. I'm into it, So the first component, the first term, you don't need the product rule on taking the derivative of sine. It's just cos. And I'm going to pull the negative out and then do the product rule on t cos t. So the derivative of t is 1 times cos plus t times the derivative of cos, but that's negative sine. And I'll clean that up in a little bit later. Let's go ahead and take the derivative of the second component of this vector valued function. So the first term is the derivative of cos, but that's negative sine, plus, and then I'm going to do the product rule on t sine t. So I'll have 1 times sine plus t times cos. Okay. And then the last component is just a t squared. That's easy to take the derivative of, 2t. Woo! I'm going to clean this up just a little bit by distributing the negative and then just making this look a little bit prettier. This is a minus minus, which is a plus. Give me about 5 minutes and I'll be ready to talk, okay? 5 minutes, I'll be off. I'm almost done. Okay, do you guys notice some things that reduce?
The coasts.
Ooh, those cancel. Isn't that beautiful?
Yep.
Does that always happen? No, but when it does, take advantage of it. Anything else in the second component?
Sine.
Yes. Take advantage of it. It's like happy, happy. Love it. Okay. Now what? Well, we got r prime. Now what? Well, arc length is defined as the integral, and they did give us the time interval 0 to pi half seconds, and you're integrating speed, which is the magnitude of velocity. So you're like, okay. So I'm going to have this horrible looking square root. Oh my God, this is awful. This is probably not even going to be integrable. Oh my God, what am I going to do? Don't worry. This one, sometimes you do get a really nasty radical when you do arc length and you can't integrate it. So just go use your calculator. Usually though, I'll give you ones that are integrable by hand. If they aren't, I'll let you know on the quiz or exam. I'll say, yeah, it's okay to use your calculator. But otherwise, no, you got to do it by hand. I claim this is doable by hand, but not yet. We're going to do some algebra. Don't worry. So if you actually do the squaring, look what happens. Do you see it? It's going to clean up. If I factor out a t squared from the first two terms, then we know the trig identity there. And then the square root just has t squared plus 4t squared. But what does that add up to? I know I'm really fast here. You know, 1 plus 4 is 5. And then you're going to use the law of radicals, which says it's the square root of 5 times the square root of t squared. So I'm going to get the square root of 5 absolute value of t. But because t is positive, if you graphed absolute value of t from 0 to pi halves, it ends up being just t, not negative t. So you can safely replace absolute value of t with t. And then you're just going to go, oh, I can integrate that. It's just going to be t squared over 2 and evaluate him between 0 and pi halves. Shoot, I'm running out of room. And so I'll do that over here. I'll have pi halves squared over 2 minus 0. And so I'll get square root of 5 pi squared over 4 over 2. And then clean that up because that looks ugly. I don't like fractions inside of fractions. It's horrible. Final answer, arc length is the exact answer is that square root of 5 pi squared divided by 8. Weird number. So that's why I put this little comic in there. Hey, professor, I ran out of round pans. Do you mind if these pies are squared? Get it? Our pies, this pie is getting squared.
Wait, what?
This is just the comic, you know. Do you mind if these pies are squared? And so this baker, she has like pies that are square instead of round pies. And so in this answer, we had pies that are squared. So I just thought it would be funny. Okay, it's not that funny. Okay, I'm sorry, it was not that great of a joke.
It's cute.
It's cute. Okay. All right, folks, I'm officially done for today. Happy Friday.